It's an important idea. The reason it's important is because what we've just laid out right here is compound interest where we have a finite number of compoundings per year, like monthly, daily, that kind of a thing. It could be quarterly. That's oftentimes the way investments are handled. How often would you get how many times a year would you get your return? Quarterly. 4 times a year, right? So oftentimes you'll see quarterly, I'll put that in here too, n would equal a 4, okay? So we just did a little investigating, and so notice that this mess in here, including the n, is approaching, if n becomes unbounded towards infinity, then that thing appears to be approaching e to the r. So the model, let me erase some of the numeric stuff we did here. So what happens then, if n becomes infinite, then the model, the future value, becomes the initial investment, and then the whole thing here, including the r over n raised to the n, becomes e to the r, and that t is number of years is still up there. You can remember this, PERT. Future value equals p e to the rt. This is for continuous compounding. So it's an exponential function. It's an exponential function, folks, that happens to be written as a base e, kind of exponential. A graph of either of these is, this one is actually finite. This, what I mean by that, or it's discrete. It's discrete. You've got your initial investment, and after each compounding, you're going to get a new amount. It'll look like that. So that would be your compound interest formula. And they don't give you anything in between. You know, if I said I wanted to take my money out of the bank after 2.5 months, they would give me the balance that was there after 2 months if I was compounded monthly. Okay? So it's only at those points in time, and there's actually nothing in between there. It would be the value, the previous value, if you tried to take it out before the next value, before the next interest was applied. Got it? And what's the graph of this continuous one going to look like? That was a hint. It's going to be a continuous function with a domain of all real numbers. And where's it going to sit relative to this one? If this is compounded, say n equals some finite value like 12, 412, 365, where would this?
Inside of that one. Just a little bit inside of that one, right?
Right up here, right? Yeah, good. You still have the same starting amount, but you're going to get a little extra bang for your buck, and it's continuous. So if I went in at 2.5 months and I said I want my money, and it was compounded continuously, I'd be able to go in right there at 2.5 months, and they would give me my money, including the interest that had been earned even from the first to that second month up until halfway into the month. Okay? So you get a little bit extra bang for your buck that way for continuous compounding. Back when I was a kid, they had lots of clerks in the bank, and I remember setting up my first checking account, I think in high school, and I remember going in, and they would have people sitting back there with little adding machines, and they had to do all that stuff by hand. That was before we had the computers. And nowadays, they're able to do this with no clerks back there. It's just all done through the computer system. And they oftentimes will give you daily or continuous compounding on an investment. Okay? So let's do some actual problems now that we maybe have a grasp on the theory. Okay? let's go in and work a problem like the following. And I'll start with what they ask, and then we will embellish a little bit. Accident here one of these days with this board.
And then the school will get a new one finally.
Hey, that would be nice. Okay. Okay. Our initial investment, and this happens to be a variation on problem 16 on our book, on page 320. The initial investment is $800 at 7% compounded monthly. And the question is, after 3.5 years, how much money would we have to, the question, the way it's phrased, this is not the present value. This is not the initial value. This is the future value. We want to have this value at 3.5 years. So this is our future value. In other words, we have a chunk of money. We need to put aside a chunk of money so that 3.5 years from now, in 3.5 years, with a compounded monthly at 7%, that we end up with $800 available. Maybe to go take a trip or something like that. Okay?
Do people really plan 3.5 years ahead?
Yeah, people do. Yeah. Most of us don't. We're a little more casual about it, but some people do. Okay. Okay. Yeah. People that really play the game. If you start as a young person just carefully investing, my dad was in the military in pre-World War II in the Marine Corps, and from the time he was a private, he would take a little bit of his measly paycheck and save it. And he's done that all these years. He's 90 years old now, and my parents are quite comfortable. He, of course, made a lot more money as he moved up into the officer ranks and then went into another industry, career. But that's the key to really being financially successful in your later life and financially secure. As long as the economy doesn't collapse. Okay. So we want to figure out, we're ending up, here's our model. We need to better write that down. Here's our model. And I'm trying to always encourage you, write down what you're going to do before you start. Write down your governing model, and then put the given information into it. So they're telling us the amount of time and all this other information, and so we end up with this thing. We have $800 in the future. We're looking for the initial value, and we have this 1 plus 0.07 divided by 12 raised to the 12 times 3.5. Now I want to show you a little something before we continue with the problem. You can see your unknown in here is simply p. So all we have to do is get this number and then divide this number into the 800, and we'll end up with the value, right? Right? Okay, so that's pretty easy calculation. But what I want to show you is this number that we get from that little experiment we did a little while ago. If we just take this stuff, including the 12, like we investigated earlier. And so if I go back on my calculator and I punch that on the home screen, 1 plus 0.07 divided by 12, close parentheses, and raise this to the 12th power, we get this value. So that turns into 1.0723 approximately, raised to the t, doesn't it? raised to the t, where the t happened to be 3.5. Okay, so just the thing here that I've circled is this 1.0723 approximately, and t raised to that 3.5 power right there. Okay? Look at this number. Any idea what this is right here? The 0.0723? Yes, that's a percentage rate, isn't it? A little bigger than 7%. That's the effective yield of the investment right there. And this is, like I said earlier, you're getting a little more bang for your buck because every month the interest is sitting there, and during the next month that interest is earning interest. And then for each period throughout that year, then the investments continue to compound on one another. And that's the reason we call it compound interest. Okay, so that's the effective yield, or the effective rate of return right there. 7.23% effective yield, or oftentimes called the effective rate of return. You go into a bank or credit union and you'll see a chart where it'll tell you what the annual percentage rate, and they'll tell you what the effective yield is. Okay, let's keep going with this problem because we want to make sure we understand it pretty clearly. So we're looking for the present value, aren't we? How much would we need to invest right now? So we ended up with $800 in the future. So we have some number here, and I have to take this number then and raise it to the 3.5 power. So let me go back quickly to the calculator.
3.2767535.
There it is. Okay, thank you. So we end up with 800 is about equal to
1.27.
P times 1.2767. And you're back to a beginning algebra level type thing. And then you solve for P, so P is going to be about equal by dividing both sides by the 1.2767, 800 over that value. And so the initial amount we would have to invest is going to be 800 divided by this previous answer. Oops, I'm sorry, screwed up. 800 divided by that value. 1.2767, I believe, was approximately it. And you'll get a slightly different value because if you carried the accuracy along. So we'd have to invest $626.62 right now, so that in 3.5 years we ended up with the $800.
Why don't you just stash $800?
Lunch.
It's not
Yeah.
enough money to bother with.
Well, what if you wanted to buy a house for $80,000 or $800,000 in the future,
Guess you put those extra zeros in
now
there.
usually you take out a loan called a mortgage to do that for those large investments. But maybe for you're saving for an automobile, maybe you have an $8,000 automobile that you want to buy, in 3.5 years, an $8,000 automobile, and you want to make sure you have that much money so you don't have to take out a loan for it. Then what you'd do is you'd start with $6,266 now at 7% monthly, and you'd end up with your $8,000. Okay? What would a graph, I wanted to do some variations on this problem, but in the interest of time, it won't lend itself too well to that. But what I want us to do is to look at this, because this is what's important. Here's your initial investment right here, and this is called P, and that's your y-intercept, and this thing is growing. What would be let's say it's continuous growth, continuous compounding. Okay, we have a continuous compounding model. So the model we're using then for A is going to be what? PERT, PE to the RT. There it is, PE to the RT. So if we have continuous compounding with some initial investment, then what might you be interested in general in the future regarding what I'm trying to get at is doubling time, tripling time, that kind of a thing. Those are kinds of rules of thumb that we oftentimes use for investments. So you can look here and see that if you're up to twice your initial value, this is going to be 2p, and there's some doubling time. Let me call that t sub d. Here is t sub d, doubling time. Let's solve that problem real quickly. Do I have a minute or two left or not? No, I don't have time. Well, I'm very excited, but what we're going to have to do is wait till we're going to have to wait till the next session to do this. But what you're going to end up with is the following: your future value is going to be 2p, and this is going to be equal to PE to the RT, and that's going to be t sub d now. And if you divide both sides by p, you end up with an exponential equation, don't you? Where t sub d is up in the exponent. Between now and the next session, why don't you go ahead and work on figuring out that doubling time for this problem, and you'll have a general formula for doubling time. Okay, that's it for today, and we'll see you next session. Later today.